Let's now take a look at sample problem 23.1.1. Take a moment to look at the description of the problem. Pay attention to the terminologies used. So we'll be looking at a Gaussian surface in the form of a closed cylinder. So if you scroll down, you can see that the integral has a little circle in it, which means we're going to be looking at a closed surface. This Gaussian surface is sitting in a uniform electric field. And from the diagram, we can see that the direction of the field is pointing to the right. The problem is asking us to calculate the net flux of electric field through the cylinder. And we will start by taking a look at the diagram. Now you want to recall the highlights of the previous video, in particular, this diagram. And what did we say about this diagram? We said that no matter where you looked at, there are always going to be two vectors, the vector E and the vector delta A. And in that diagram, they gave us three locations. There was the situation 1, the situation 2, and the situation 3. And it so happens that in the current problem, we also have three situations to look at. And that will be the one on the left, the one in the middle, and the one on the right. But let's take a step back and look at the cylinder itself. The cylinder has three surfaces: the circular surface on the left, the circular surface on the right, and the surface in the middle. And once again, let's recall that this cylindrical surface is sitting in an electric field that is pointing to the right. With that, let's now look at the circular surface on the left, corresponding to the situation 1 in that earlier diagram. Now, remember that this cylindrical surface is a closed surface. This is actually important because if the surface is closed, then the surface area would always have a direction that is pointing outwards. And therefore, for the circular surface on the left-hand side, the direction of the surface is pointing to the left. You can also look at the circular surface that is on the right-hand side. There you can see that the direction of the surface will be pointing to the right. And of course, in the middle, the direction of the surface will be pointing away from the axis of the cylinder. Let's now look at how we can calculate the electric flux. We'll start from the left-hand side. For each surface, we'll be looking for the two vectors, E and dA. And we are going to form a dot product using those two vectors. Since we'll be doing an integral, so let's turn that delta into lowercase d. And for each vector, we have written the vector in its component form. And the result of the dot product will be obtained using the formula that we used earlier. You can use the first definition if you like. The result will be the same. Notice that after the dot product is obtained, the result is a scatter. Now that we have an expression for the differential electric flux, we can go ahead and do the integration. Since the electric field is a constant, it can be put out of the integral, and we're going to put it in the front. We can now apply basic calculus to complete the integral. Notice that in the notation for the integral, there isn't a small circle. And that's because the surface that we're working on is not a closed surface. Let's now look at the surface in the middle. This will be a cylindrical surface. Just like before, we'll be looking for the two vectors E and dA and form a dot product between them. Since the vector dA is pointing away from the surface and therefore vertically up, and the electric field is pointing horizontal to the right, the angle in between is 90 degrees, cosine which is 0. Incidentally, we can also conclude that whenever we have two vectors that are perpendicular to each other, the dot product between them will be 0. Finishing the integral just like before, and we can conclude that for this cylindrical surface, the electric flux will be 0. The calculation for the electric flux for the surface element on the right-hand side is more straightforward. There you can see that the two vectors E and dA are each written in its component form, and we are applying the definition of the dot product using the component form. Now that we have obtained the electric fluxes for the three surfaces, we now need to add them together. Notice that in this integral, there is a small circle in the middle, and that's because we are now doing the integral over the whole Gaussian surface, which is a closed surface. Adding the three components together, and we will obtain the result, which is 0. So, in summary, for a closed cylindrical surface sitting in an electric field, where the direction of the field is parallel to the axis of the cylinder, the net electric flux is 0. And that completes this video.